Okay, welcome back. Today we will be talking about the natural exponential function. We talked about exponential functions before. 2 to the x 4 times 1/2 x and so on. So we have an initial value, we have a base, okay? And depending on the base, it will be increasing for 2 to the x and decreasing for 1/2 x. So that's what we know before. Now you receive a very interesting question, that is, how do you compare exponents? For example, which one is bigger? 2 to the cube and 2 to the fourth. We know, of course, 2 to the fourth is bigger. Now, if you think about it, we are going to have something called 2 to the 7 and something which is called 4 to the square. Which one's bigger? Now it's kind of trickier, right? Without computing, what we notice is actually, well, wait a second. 2 to the square, 4 to the square, and 4 equals 2 to the 2. So I can do this first. And once I see, okay, if these two have the same base, I can compare exponents directly. So it's way better when we compare two exponents if they were written in the same base. Okay, is that possible? Well, if you have something 2 to the 8 to the square, you can convert it. Okay, you can convert it to be 2 to the cube to the 3, which is 2 to the 9. You can also convert it to be base 4. That is 4 to the, think about it, you take the square root first, and then you cube it to the cube, which is 4 to the 9 half. Okay, from here we can see for the same exponents, we can actually change it to be any other exponents, as long as we change these two numbers to be the corresponding pair. Can we even change it to be 3 to some power? Or maybe 1.5 to some power? The answer is yes. The only trouble is the number here won't be pretty. It may be something like 3.1.7234 equals 8 or something like that. We need some additional techniques to find this number here, and it will not be pretty because 8 and 2, 8 and 4, they have integer relationships, but 3, we don't. Okay, but the idea is similar. That is, for any exponent, okay, we can actually have the freedom to choose whatever base we want. Okay, even if everything is written in base 8, we can change it to be base 2, base 4, base 5, base 3 to our convenience. That is great. Second, for different exponential function, different exponents, we really wish they all share the same base. So how about for any exponential? We all put them on the same benchmark by choosing the same base. We choose the same base. Then, to compare which one is bigger, we just need to compare, okay, are you a 3 power, are you a 3.5 power, are you a 2 power, which is very convenient. Then, since we're doing this thing once for all, we better choose not just the same, we want to choose the best base. We can choose them all to be base 3. It will be good if you're 9 or 27, it will be bad if you're 8. So who's the best base? That's what we are thinking about. And we will show it is actually the natural base. It is the best base. For now, we can only show why this one reads from natural phenomena. We probably cannot show you why this one is so convenient until calculus. This one has really a lot of nice property. But for now, let's just think about it. Just try to know it, okay? Introduce it. So why is this so special? Let's go back to compound interest. We talk about something like this. All right. Now we say we take some dollar. Okay. We can do it. Let's just take $1,000 with the annual rate 12%. Okay. Then we say how much money we receive really depends on how many times do we compound. Okay. So let's just consider 1 year. So what we're going to get is, we are going to get 1,001 plus 12% for once if you do it annually. Okay. We will get this much. Actually, let's switch how we write it. I want to put this one here, this one here. Annually, we got this. We do it seasonally. We have this with a 4. And as we suspected, the more times you compound, the more money you got. Now we got monthly. Which give you a 1% per month, but 12 times. We don't have to stop there. We can do it daily. What do you do? This many rate, that's your daily rate for this many days. Good so far? Okay. Now, actually, this is how people do insurance and everything here. If you just, stop your insurance on March the 14th, they will actually refund everything after March the 14th. You don't have to pay the full month of March. So that's very, very advanced, which is very nice for us. Okay. But we don't have to stop there either. We can do it minutely, secondly, which means every second you just compound. You can write down the formula. It's not hard to do. All you need to put is how many minutes are there in a year, which is this many days, and each day this many hours, and this many per hour. That's not a pretty number, but it's not too bad either. Okay. Secondly, okay, you basically take every number you got before for minute times another 60. That's how much you're going to gain in 1 year. And what did we say? We said the more times you compound, the more money you're going to make. So these numbers just keep getting bigger. Question. Where is this one going? You can do it 10 times per second. You can do it 1,000 times per second. And eventually, we end up at the limit. That is something we call continuously. That is every time there is a change in time, no matter it's like a millisecond, 1,000th of a millisecond, as long as you changed, you blinked, the money change. Okay, so eventually that's where the limit is. I'm wondering, this one, if this one keeps increasing, okay, when will be this limit? Is it going to be infinity without bound? The more you do, the better. Okay, eventually you can actually take $1,000, but if you compound it for infinite many times in a year, you will receive $1 million. Is that possible? Let's try to do the calculation and let you see the trend. This is 1,000. Very easy to do. This, let's take a calculator. 1,000 times 1.03 to the 4. This gives you 1125. Let's keep it decimal. .501. It's 509. You earn $5 more by doing it seasonally compared to annually. Now, this one for 12 times. That's gonna be you spend 4 times more trouble, you gain $1 more, $1.3. Fine. But now let's do it daily. That's another lot of trouble. You gain this much. $1 and actually 0.6 some cents. Going from here to here, you earn 5.5 more. From here to here, you earn probably $1.325. Not $16. Keep going. You spend more trouble by doing it minutely. Which will give you 1127. Okay, which give you this much more. Now if you take additional trouble to do it every second, you receive this. Actually, you receive the same thing. The difference are actually in the decimals after this. So it's very little tiny difference. From here we can see, well, technically you can compound more and more times, and eventually you compound infinitely many times a year, which means continuously. But still, you are not going to get more and more money. It seems like you stop roughly at 1127, 497 actually. So this gives us a very interesting thing. That is, this limit process gives us a fixed number. That number is related to the natural base e. And let's see how we define it. This is how we do. We can take any principles. We can take 1,000, we can take 2, we can take 3. To define some natural number, we better take 1 unit. So we take $1. We can have any annual rate. Okay, but let's just take the rate to be 1. We can take 0.10, we can take whatever we want. But to make it unit, it's going to give us something standard. And within 1 year, we're going to do it for n times. Okay. Simplify a little bit, this one doesn't count. Now what we want to do is, we want to let n goes to infinity. This is called taking the limit. This is the notation, which means let n goes to infinity. To get a sense, you can take out a calculator and try to calculate this number, and then make it 100, make it 1,000, 1,000,000, and keep going. I will skip the part. But eventually, your calculator, or through mathematical computation, they goes to a fixed number, and we call that number e. Which is 2.718 something. We will just roughly say it's 2.72. That is the definition of a natural base, this weird number. Okay. The definition is through a limit processing. It comes from compound interest, and eventually you push it to compound infinitely many times a year, which means compound continuously. You got e. Okay, that's the definition. Now, second, e is a irrational number. So it's not a fraction. It repeats forever for the digits, and it never repeats itself. Okay. The last time we know some irrational number, which also is very natural or deserve a very important position, that one is called pi. Okay, so from now on, every single time you see e, you just know it's similar to pi. When you see pi, you reflect to 3.14. When you see e, you reflect to another number, 2.72. Okay, there's no meaning for this letter, only represent that special number we're looking for. That's e. Okay, great. If we have the natural base, we now can define the natural exponential function. That is given by y equals e to the x. It's very easy. No. Y equals e a kx. Here a is the initial value. Okay. K is called the continuous growth rate. It can be positive or negative. If k is bigger than 0, we have a growth. If k is less than 0, we have a decay. That's the natural exponential function. So for example, if you have y equals 2 to the x, Remember, we're saying this one is the uniform base. You should change it to be y to e to some x with a certain rate. We just don't know how to find this rate yet, but later we will show. If y is 1/2 x, you are going to have y equals e to the something x. Again, this rate should correspond to the base 1/2. Moreover, this should be bigger than 0. This should be less than 0. Because y is decay, y is growth. That is very convenient. So next time if you want to see something is growing or decaying, how much faster each one is growing or how fast each one is growing or decaying, you simply just look at this number here. Positive, grow. Negative, decay. Big number, faster. Okay, so that's good. That's the definition of exponential function. Second, it corresponds to continuous growth. Or at least for now we can talk about continuous compound interest. What do you mean by that? We had a formula before, which we call discrete. We have a p 1 plus r over n nt. Now we have a new formula which is continuous compound interest, which is the principle. Now we let n goes to infinity. We already know the limit, so clean things up, we have this final formula given by this. So next time in a problem, if you see a discrete and you were given seasonally or monthly, you go with discrete. But if we tell you it's a continuous growth model, you should use this formula instead. Okay? That's the continuous compound interest. So number 3, of course, we want to talk about continuous growth, decay model. And that is given by the examples we had before. Continuous compound interest is certainly one. Okay. Population growth is another one. You think about it. It does not make sense to assume your population grow annually. That means people are only allowed to have a baby on January the 1st. Or December the 31st. I don't quite remember. January the 1st, I would say. Right? That means every year at a fixed date, everybody give birth for once, and then we wait until the next year. It's not the case. In real life, it's more about like you can be born anytime. So anytime you're growing the population. Right? So that's why continuous growth is better for population growth. Because it can happen anytime. It's not like the compound interest. You can artificially to say anything before January the 1st doesn't count. Okay? For population growth, you only do the compound interest on January the 1st, right? But for population growth, you cannot restrict that. Similarly for radioactive decay, it's decaying at every moment. Therefore, a continuous growth rate is more accurate. That's why in real life, other than compound interest, probably it's very rare for you to see anything that is not decay or growth at a continuous rate. That's it. That's everything we need to know about natural exponential function. Now let's use it to do some examples. Let's take lacrosse. Population. Okay. Now we know at 2020, the population is 50,000 people. Okay. My question is, what's the population at 2025? And what's the population if you backtrack at 2008? We want to know that. Moreover, we need two assumptions. The first one is assuming the population grow continuously. Second, the continuous growth rate is 0.5, measured in year. That is, your population keeps growing, you have a continuous rate. Moreover, that is equivalent to 5% per year. So if you just let the population continuous growth for a whole year, you gain 5%. But it does not happen at January the 1st. It happens at any time. How do we solve this? All right. This is the formula. Now all we need to do is we need to, number one, pick a principal. Since we already know for 50,000, I will pick the principal to be 50,000. $20, therefore P equals 50,000. Then our A is 50,000. E to the R, which is 0.5 T. Once we set it up, to know the population of a certain year, you just need to plug in the number for T. For 2025, if we use 2020 to be the principal year, that means T equals 5, which means 5 years after 2020. For 2008, if you use the baseline to be 2020, that's going to be 12 years ahead of time, so you need to plug in -12. With that in mind, use a calculator, we can calculate it. 50,000 e to the r times t, which is 0.25. There are some decimal, we just round it. Okay, we're talking about people here. So that's the population we expect to receive within 5 years. -0.6. Roughly this. Okay, from here you can see it's very convenient. As long as you have a baseline, in this case 50,000 people at 2020. So as long as you have a principal, which is your baseline, and as long as you know R, which is your growth rate, you can either forward track or backward track. Either way, you can find the population along the line, which is very convenient. If we assume everything grows exponentially and it grows continuously. All right. That's it. That's everything we have for natural exponential growth. Now, naturally, we have a question. These data are all given by the problem, but in real life, you actually start to wonder, how did you get this 5%? You cannot just track people and measure them continuously, right? So instead, what you do is the reverse. What you do is you do this. Lacrosse population. What you do is you measure in 2020 and you measure in 2008, because the population is way easier to measure than the growth rate. So instead of observing the growth rate directly, you measure the function at the 2 point, and in this way you want to calculate the growth rate. That's the right way of doing stuff in real life. That's actually how people get the growth rate from the beginning. You don't observe the growth rate, you calculate it. Now how do we do this? Well, we can take a baseline. We can take it to be 2008. We don't have to. You can take this to be 0 and this to be -12. Or you can take this one to be 0, this one to be 12. It's all relative. I personally prefer to take the earlier year to be the baseline. So P equals, this is the model. Now what we can say is, R we don't know, but we do know it takes us 12 years from 08 to 2020. To grow from this number to that number. So finally what we end up with is, which is a number, which is another number here. So in order to continue, what do we need to do? We need an operation to calculate this number from this number. That's the operation we need. Now think again, what do we have before? We have 2 to the x, which is exponential. That means if I know this number, I will know this number. If I know it's a cube, then I calculate through the base 2, I will get this number is 8. Now if you observe what we have here, we have the reverse. We know this number is 8. Can we go back and figure out what this exponent is? If we know this number is this weird number, can we know what exponent is given the base e? Make sense here? So what we need is actually, if you think about it, exponential function we know how to get here. Now we're just wondering how to get from y to x. We need something called the inverse function of the exponential function. That is called the logarithmic function, which will be the second half of what we have for chapter 4. Okay, that will be all for today.